Hello students, in this session we are going to study the Euler's theory of column, the one end fixed and other end free. So we have another case that this is our column in which one end is fixed and other end is free, and you know that when one end is fixed and other is free, there is some deflection, in the axis, and there is bending is there, and there is zero slope at this point. That's why you will see like this. This is the variation, this is the change in the deflection in the column, right? And we have applied load here P, and this load will move to this position, right? So final this position is there, this is the final position, right? So this is the bending in the column, right? And this end is fixed, this end is fixed, and the slope at this point is theta is 0. You know that already, we have studied the boundary conditions for that. And what are the boundary conditions for that? Boundary conditions, say this is some deflection in y direction, that is A, and we want to find out this y, this the deflection in this point, let's say C, and this is D point and this is E point, and what is the deflection in y at a distance x from the fixed end, right? This we want to find out, right? This deflection y, right? And the boundary conditions are, you must remember, boundary conditions are, first boundary condition is that x is equal to 0, y is equal to 0. There is no deflection in y direction at this point, D point. So x equal to 0, y equal to 0. What is second boundary condition? The slope at this point is 0. That's why you are seeing that this is there is zero slope, right, at this point, right? The straight line, slight straight line is there. So x equal to 0, dy by dx, the slope equal to 0. And third also you can use, if required, that at this point x is equal to L, say this is the length of this column L. In the length of this column x equal to L, the deflection y will be equal to A, right? So this is the boundary condition which will be required for solving the unknowns A and B constants, right? Now what is the deflection equation for this? Deflection equation, we know that EI d2y by dx square will be equal to the bending moment. Now what is the bending moment? Bending moment is, you see here, this is P, load applied is P multiplied by this distance. This distance is this distance, you see here, perpendicular distance, this distance, this which I have shown here, this distance, this perpendicular distance. And what is this distance? This is A minus y, right? So P multiplied by this distance, A minus y. Is it okay? So we are finding, and this is positive, because the convex case we are taking the positive according to our sign convention. So it was our sign convention that for convex shape we will take the positive bending moment, right? So this will be equal to P times positive multiplied by distance, that is A minus y. So from here we can solve it somewhat, that EI d2y by dx square plus Py equal to PA. So d2y by dx square plus P by EI y, that is equal to P by EI multiplied by A, isn't it, right? And say this P by EI is given by some another value, so that the solution may be simplified. So let us say this P by EI is given as m square. This we will be using in this differential equation. So we can write d2y by dx square plus m square y is equal to m square A. So this is the equation. This is the equation which we have to use to find out Euler's load for one end fixed and other end free, right? So d2y by dx square plus m square y is equal to m square A. So this is the first equation, right? And what is the solution of this? Solution, you must know the solution of this. Mathematically, you know the solution. Check your mathematics and find out the solution. So you will get the solution as, you will get the solution of this equation as y equal to a sine, this m square will become m, so mx plus b cos mx plus m square a divided by m square. You know that you should know that this term is divided by the term which is in y, right, which is the constant of y. Constant of y is m square. So m square a divided by m square, it will come to a only, right? So it will become a. So this is the solution of this differential equation. Go to mathematics and check how we have obtained this solution. Y is equal to a sine mx plus b cos mx. Now we want to find out the Euler's load, this load P. This load P we want to find out, but we require two unknowns to be removed, A and B. So how to find out unknowns A and B? So to find out unknowns A and B, use the boundary condition. First boundary condition is x equal to 0, y is equal to 0. So first boundary condition is x equal to 0. In that case, y is equal to 0. When x is equal to 0, that point deflection is 0. Y is equal to 0. Put in this equation number 2. Put in this equation and you will get some solution, or one of the constant will be obtained. So 0 will be equal to a sine 0 plus b cos 0 plus a. Sine 0 is 0, cos 0 is 1, so b will be equal to minus a. So you will get one constant as b is equal to minus a. This is one of the constant, b is equal to minus a, right? So you have obtained one equation, b is equal to minus a. Now what is second boundary condition? That x is equal to 0, slope will be equal to 0. So x equal to 0, slope will be equal to 0. So second boundary condition is x equal to 0, dy by dx will be equal to 0. And what is dy by dx? What is dy by dx? If we got the dy by dx, here I want to make so that this space can be saved. What is dy by dx? Dy by dx is the solution, differential of this equation, right? Differentiation of this equation. So a m cos mx, differentiation of this b cos mx is, differentiation of cos is sine, so you will get minus b m sine mx, and differentiation of a is 0, so this will be the differentiation. And this is, if this is the differentiation of y with respect to x, then use it, this is suppose equation number 3, use it in this equation, that x is equal to 0, dy by dx is equal to 0. Put x is equal to 0 and dy by dx equal to 0. What you are getting, that 0 will be equal to am cos 0 minus bm sin 0 minus bm sin 0. Sin 0 is 0, cos 0 is 1, so am will be equal to 0, a cannot be equal to 0, a cannot be equal to 0, so it means no, a can be equal to 0 because b is not equal to 0, that's it, a can be equal to 0, right? So cos 0 is 1, this is 0, m cannot be equal to 0, this cannot be equal to 0, so a is equal to 0 here, a equal to 0, right? So b is equal to minus a equal to 0. Put this in two equation, put in second equation, here also put in second equation, and what you are getting now, you will get the new equation, that y will be equal to a sin mx, a is 0, leave it, b cos mx, b is minus a, so this is minus a cos mx, and minus a, b become minus a cos mx plus a. So this is the new equation. Suppose this is equation number 4. Still we want to find out this load P. What is this load P? For this we can apply the third boundary condition also, that x is equal to L. At this point deflection is A. So deflection is A at cos ml when x is equal to L. We have put the value of x as L. This is x. Value of x is now L and the y will become A, right? Solve it and what you are getting is that this A will come out here, cos ml will be equal to 0. So you are getting that, what you are getting is now, you are getting that cos ml will be equal to 0. And when cos ml is 0, at what condition cos ml is 0? When this is cos pi by 2. Pi by 2. We are taking the minimum value, cos pi by 2. It means that ml is equal to pi by 2. ml will be equal to pi by 2, or you can write m square l square will be equal to pi square by 4. Pi square by 4. So you are getting m square l square equal to pi by 4. And if you are getting m square l square equal to pi by 4, m square in terms of force P is P by EI. Put the value of m square. So what you are getting is P by EI L square equal to pi square by 4, right? So from here you will get the load, Euler's load P E equal to pi square EI upon pi square EI upon 4L square. 4L square. So this is the Euler's load for, and this is very important, you have to remember this. So this is the Euler's load for one end fixed and other end free, that PE will be equal to pi square EI upon 4L square. So what we have done in this case is, we are using the one end fixed and other free, and one end is fixed and other is free. These are the boundary conditions. Using these boundary conditions we have found out that finally we have got this solution of this differential equation, and put this boundary condition in this equation, you will get the load PE as pi square EI upon 4L square. So this is the solution of this problem, that one end fixed, other end free. The Euler's load is given by this equation.